Okay, I think I have to accept the terms and conditions. I hope I got it right. Okay. Hello, everybody again. Yeah, no need to introduce myself. Thanks to gentle introduction. The title of my talk is Train Nanomechanical Resonators with Ultralow Dissipation for Quantum Optomechanics. Yeah, if you want to stop me to ask some questions.
So my first question is, I think we don't see your screen yet, or?
I should have shared the screen. It's not working.
So I don't see it. What about?
Yes, I think now you see something, right?
Yes.
Okay, and if I now start the presentation, you see it, and I should swap to slideshow view. Now you should see the slide, right?
Yes, perfect.
Okay, great. So yes, as I was saying, please feel free to stop me if you have any questions or curiosities. Maybe it's going to be a bit, the seminar is going to be a bit superficial level for you, since you already discussed and you're very expert in nanomechanics. So we can make it more interactive, or please feel free to stop me for any questions you might have. So just as a brief introduction, recapping why mechanical oscillators are very ubiquitous in all fields of science and technology. To my understanding, it's basically because they are capable of coupling with many different systems and many different force fields. And this makes them, for example, very useful for precision sensing of all sorts of tiny forces. For example, for not so tiny surface forces, they're used in atomic force microscopes, or for very tiny forces to detect magnetic forces induced by magnetic resonance in MRFM techniques. And they can be used also in mass spectrometry, for example, for detecting and resolving the mass of small biological samples, such as bacteria or viruses, by recording in real time the resonant frequency of some mechanical resonance and seeing how it shifts. Corresponds to the absorption of some biological sample. And then they're of course ubiquitous in all sorts of electronic devices and gadgets as accelerometers. And for example, the performance of such accelerometers have been shown to be improved by cavity optomechanical detection techniques. Also in quantum technologies, mechanical oscillators are becoming more and more common, a more and more common sight. Again, due to their capability of coupling with many different force fields. And for example, one can use piezoelectricity to couple with superconducting qubits and implement, just as an example, long-lived quantum memories for quantum information, or quantum information stored in a superconducting qubit. Here, exploiting the typically much longer lifetime of a mechanical oscillator compared to the lifetime of charged qubit or transmon qubit, superconducting qubits typically. And another very hot field of application is for a frequency transduction between microwave and optical domains, because it's easy to couple a mechanical oscillator, for example, a membrane mechanical oscillator, with both a microwave cavity and an optical cavity at the same time, as in this work. From a more fundamental point of view, mechanical oscillators are quite commonly used for tests of fundamental physics, or to test candidate theories or predictions. For example, to test postulated models of wave function collapse, or that describe how and why the wave function of a quantum system would collapse when the system is measured or interacts with an environment. And here, people have used both nanomechanical oscillators and are trying to use levitating nanoparticle systems in magnetic traps or optical traps. And also, of course, in gravitational wave interferometers, sense the arrival of gravitational waves from astronomical events on Earth. One uses the motion, one detects very precisely the motion of some test masses, which are typically the end mirrors of the interferometer placed at a very large distance and placed inside some optical cavities. And yeah, for all of these different applications, I've just examples that I've mentioned. The quality factor of a mechanical resonance is an extremely important figure of merit. I don't even need to introduce the quality factor, okay? But it appears, yeah, basically the quality factor is the number of oscillations, proportional to the number of oscillations that a resonator will undergo before when it's excited and before it decays to its equilibrium state. And it appears both, for example, in the thermal decoherence rate, which is very important figure of merit for cavity optomechanics experiments, and in the thermal force sensitivity as set by the fluctuation dissipation theorem. So the minimal force that can be resolved by a mechanical sensor due just to its fundamental thermodynamic fluctuations. And in both these quantities, we see either the quality factor or the damping rate or the inverse quality factor appearing. So it improves all these, for sure, all these applications that I've mentioned. In our lab, we use a set of techniques to improve and engineer artificially the quality factor of mechanical oscillators, of nanomechanical oscillators, beyond the intrinsic properties that the intrinsic material friction supported by the material that we fabricate the nanomechanical oscillators with. And actually, this phenomenon of dissipation dilution was first understood and used in these massive end mirrors of gravitational wave interferometers, where you have mirrors with masses in the scale of tens of kilograms, which are suspended by thin silica fibers and stretch them under tension. And here the description of the improvement of the quality factor is intuitively because one can store mechanical energy in a lossless way, in a totally lossless way in the gravitational field, acting on the mirror mass. And the gravitational field is completely conservative. Therefore, it modifies the resonance properties of some flexural resonances of these silica suspension fibers without introducing more dissipation. The same phenomenon has been later, like let's say 1 decade later, discovered and understood to set the dissipation properties of high aspect ratio mechanical oscillators fabricated out of strained thin film materials, and where the strain can be pretty naturally obtained by the growth or synthesis properties of thin films. And here, the enhancement, the dissipation dilution can be seen to be due both to the stress in the thin film and due to the geometric nonlinearities present in the vibrational mode pattern, as we'll see now with a simplifying example or toy model. This is a toy model, which is very simple, but contains all the essential features for dissipation dilution. We can consider a mass which is suspended by 2 idealized 1D springs. And the springs are not simply at rest, but they're stretched, they're elongated by a quantity, by an elongation delta L in static conditions, in stationary conditions. Then we want to explore, to study the vibrational properties of the system, and we can write such an Hamiltonian for the mechanical oscillations, where if we diagonalize the Hamiltonian, we see that we'll have one mode polarized along X, so one longitudinal mode, and another mode polarized along Y, a transverse mode which displaces the springs in the transverse direction. And also from the Hamiltonian, we notice immediately that such a transverse mode where the mass is moving along Y is a so-called floppy mode in the absence of strain. That means that the frequency would be 0 in the absence of static strain of the springs. And it costs no work in practice to displace the mass in the Y direction, because these are idealized 1D springs. But the presence of the strain is very important because it introduces a finite resonant frequencies for the Y mode, for the transverse mode. Now we want to study the dissipation properties of such vibrations. So we introduce formally a viscous element, a simple element called a Voigt damper that basically introduces a dissipation which is proportional to the velocity or the rate of change of the elongation of the springs. We put it one in parallel to each of the springs, and then we compute the quality factor by the definition, basically. So the ratio of total mechanical energy of the oscillation motion divided by the energy lost in a single cycle, in a single period of oscillation. And then we can compute it, for example, for the longitudinal mode. We'll recover the quality factor, which is exactly the inverse of the loss angle corresponding to the Voigt damper. So basically exactly what is set by the friction properties of the damper that we put on each spring. But for the transverse mode, polarized along Y, something completely different happens, because here the spring is no longer, the spring elongation is no longer linear in the displacement, but it's quadratic in displacement due to the geometry of this displacement, of the so-called geometric nonlinearity that I was mentioning before. Since it's quadratic, the denominator of this expression, so the energy lost, will scale faster in the amplitude of oscillation than the numerator. And then we get a dependence on the inverse of the square of the amplitude of oscillation. So in the limit where we have a small amplitude of oscillation, the quality factor will diverge, will go to infinity in such a resonance. And we see also the importance of the static strain. Otherwise, we wouldn't even have properly defined the mechanical mode in the transverse direction. So this was it for the idealized toy model, but we can also compute the dissipation dilution that we would expect in high aspect ratio nanostring or membrane devices, in nanomechanical oscillators. And it's no longer diverging in the limit of small oscillation amplitude, but it's finite. And specifically, it can be expressed by some simple expression like this, where the quality factor is proportional both to the intrinsic quality factor of the material. So it's one component of it. It's set by the intrinsic material mechanical loss. It's proportional to the effective stress in the nanomechanical device in equilibrium. And then at the denominator, we have the geometrical contribution of the mode pattern, let's say. So we have an integral basically over the square of the curvature of the mode shape. And here the integral it's convenient to split into two different contributions. One part of the integral is carried out on the boundary, close to the boundaries of the nanomechanical oscillator, because close to the boundaries you have sharp curvature introduced typically by the boundary conditions. And then we have a particularly high contribution coming from the clamping regions. And then we carry out the second integral on the rest, on the bulk of the surface of the mechanical oscillator. And this splitting of the denominator is convenient because it's easy to see that one part will depend on this infinitesimal parameter lambda. Lambda is this parameter which is much smaller than 1 in practice, which is inversely proportional to the aspect ratio of the structure. And this clamping region's contribution is simply proportional to lambda. The bulk contribution is proportional to lambda square. So since lambda is much smaller than 1, typically the first contribution will dominate. The clamping points contribution will totally dominate over the bulk contribution, at least for the lowest order resonances. We can also see that if you find a way to engineer the mode pattern such that we don't have a strong or sharp curvature close to the clamping points, so we can kind of create artificial boundary conditions, then we can get rid of this first term in the denominator, and we can get a much better scaling with lambda, which corresponds to a set of techniques called soft clamping that have been developed in the latest years in the nanomechanics community. And then if you look, this is just a small timeline of roughly the highest quality factor mechanical oscillators that have been measured over time or reported over time since the discovery of dissipation dilution in 2006 in silicon nitride nanomechanical strings. and it's quite remarkable that over a period of 15 years, basically there's a 3 orders of magnitude improvement in the highest quality factor reported, going from this discovery in silicon nitride strings to the discovery that it also takes place in some commercially available silicon nitride membranes that are used for were used for the purpose of transmission electron microscopy as a window for electrons, basically for microscopy experiments. And then later on, new designs of mechanical oscillators have been devised, including the discovery of soft clamping in 2017 and other soft clamping implementations and techniques since then that continued the trend, basically. And again, we can distinguish two main contributions in the quality for the overall quality factor. One is a so-called dilution factor, which depends on the stress, the static stress established in the nanomechanical structure and on the details of or in the geometry of the mode shape pattern. And we have another contribution due to the intrinsic material properties of the or the material friction for the material that is used to fabricate the nanomechanical resonators. So this is basically the inverse of the material loss angle. And for this work that I'm going to talk next, or that we're mostly going to talk about in this seminar, we wanted to find a way to retain a high dissipation dilution while improving on the intrinsic quality factor of the nanomechanical oscillators we fabricated beyond the one of silicon nitride that was in general most commonly used for all these demonstrations or all these dissipation diluted mechanical resonators. We decided to work with crystalline silicon that is strained to high levels of strain around 1% or 1.2% in our samples, and correspond to a stress levels of around 1.3, 1.5 gigapascal in the strained silicon layer. And it was quite convenient for us to start with this material because it was easily available from company called Soitec in silicon on insulator wafer stack. So basically we have around 12 nanometers thin film of strained silicon bonded on top of silicon oxide, sacrificial layer around 140 nanometers for these substrates. And then the wafer itself is made out of silicon, of crystalline silicon. This wafer stack was actually high or very large commercial impact or interest because it was widely used in microelectronics because the stress induced the deformation of the crystalline lattice of silicon allows to engineer the carrier mobility of electrons and holes. Basically, that one can then create engineer MOSFETs or transistor in general with a higher carrier mobility, which corresponds to better frequency response properties. And actually, even the MOSFETs, the digital MOSFETs that are built nowadays, up to my knowledge, are made out of strained silicon, but maybe not out of this epitaxially strained silicon, but out of externally strained silicon. They may fabricate some special straining or stressor layers to artificially introduce the strain in the channel. And also either with this epitaxial techniques or with the stressor layers, one can, if one introduces some strain in a silicon thin film, one can also break its inversion symmetry, for example, therefore allowing to create a Pockels coefficient or a Chi2 nonlinearity for optical waves, which has allowed some researchers to create or to build electro-optic modulators out of silicon, which usually doesn't have a Pockels coefficient when it's not strained. But for our purposes, we were mostly interested in the potential potentially very high intrinsic quality factor demonstrated by single crystal materials. For example, here we can see some plot of the measured quality factor versus temperature at liquid helium temperatures for a macroscopic single crystalline silicon oscillator already in the 70s. So it was already realized since the 70s, both in silicon macroscopic oscillators, but also in sapphire or quartz macroscopic oscillators that single crystalline oscillators can have extremely high quality factors beyond 1 billion at cryogenic temperatures. And they have been, for example, used for implementing these prototype Weber bars that were candidates for gravitational wave antennas, but in the end didn't work out. So we started with this strain silicon on insulator material platform, and we wanted to create to exploit dissipation dilution. We want to create some high aspect ratio nanostrings. So we had to develop a way to suspend these nanostrings. And the first challenge that we had to face was that we couldn't use just the silicon oxide layer to suspend the nanostrings because it's too thin. It's just 140 nanometers. And if you just suspend them by removal of the silicon oxide sacrificial layer, they would instantly collapse on the substrate. Then we had to find a way to excavate the substrate and create a higher recess directly in the silicon substrate to suspend like some tens of microns to suspend correctly without stiction or collapse the strain silicon nanostrings. So the fabrication process we devised is as this. We first pattern with electron beam lithography the device layer of strain silicon. We make some nanostrings with electron beam lithography. And then we basically deposited a stack of insulating materials in order to protect and cover the strain silicon nanostrings and protect them during the subsequent depatch and undercut steps, because basically there's chemical identity between the substrate material and the nanostring material. So we use SF6 for the undercut of this encapsulation structure, and we would, if we didn't we didn't precisely protect the nanostrings, we would completely etch away the strain silicon layer in this step. So we have to make sure that they're properly sealed and encapsulated during this step. And another important caveat is that we need we have another requirement from the encapsulation layer stack, that we must compensate the compressive stress naturally present in the silicon oxide layer. So if you grow silicon oxide, it will have a pretty strong compressive stress around minus 300 megapascal. And if you just suspend the high aspect ratio structures with that, typically you get buckling or just buckling instability. And eventually, if you make even higher aspect ratio strings, they will just collapse completely. So basically, we used this PCVD, a pretty thick layer of PCVD silicon nitride, which is painted in green, which has tensile stress to compensate completely the compressive stress of the buried oxide and keep the nanostrings fully flat and tensioned during the undercut process. And then the yield is excellent after this. And finally, in the last step, when the strings are suspended, we remove the encapsulating layers with selectively with a dip in hydrofluoric acid, which doesn't touch at all the silicon nanostrings. And then basically we have to dry. After this step, we also have to dry in critical point drying the nanostrings unless we want them to collapse. So I have to remark that this fabrication process, which is slightly involved, a bit complicated, but in principle, it's not necessary. If one finds a method to bond strain silicon on top of a much thicker sacrificial oxide layer. So if you started out with several microns of sacrificial oxide, you would be able to undercut the strings simply in vapor HF, for example, and then the fabrication process would really be extremely simple, just a couple steps. Vapor HF also doesn't present stiction, so it would work out perfectly. So I think so. Yeah, but we started out with this particular wafer stack, so we worked with what we had. So after fabrication, we wanted to assess that the strain silicon layer is fully crystalline and not affected by the various fabrication steps. So to do this, we prepare some we slice some thin lamellas out of the samples that we fabricated, and we put them in a transmission electron microscope, and then we can observe with this electron microscope, we can observe nicely the presence of I mean, we can characterize the crystallinity or the grain boundaries, for example, of the strained silicon thin film. We can resolve easily the atomic lattice in a strained silicon layer, whereas we don't get any kind of atomic lattice resolution in the amorphous silicon oxide or platinum that is used for contrast around. Also, we can see the presence of relatively thick native oxide around strained silicon, around more than 1 nanometer around all the exposed surfaces, which is also amorphous. We could then use another interesting technique to characterize the strain in the strained silicon film in electron microscopy, which is called dark field electron holography, which basically it's similar to optical holography in a sense that you do some interference between 2 electron beams, one of which is transmitted through the unstrained silicon substrate, and one of which is transmitted through the strained silicon layer, and you interfere them at the detector using a electrostatic element called a biprism that basically focuses the same deflects both the electron beams on the detector. And basically, because you have different lattice constant in the silicon substrate and in the strained silicon layer, you will get different diffraction patterns corresponding to some moire fringes on the detector. So you will see some fringes at the detector, and the interesting part is that the spatial phase of these fringes is proportional to the atomic displacement in the strained silicon layer. So with a relatively simple algorithm of reconstruction, one can find out the strain, find locally the strain of present in the thin film. And here one really has nanometer scale resolution with this technique. And we can also nicely see that there is absolutely no fringe contrast in the amorphous regions up above and at the bottom of the strained silicon thin film. So here we reconstructed a strain of average strain of around 1.2%, if I remember correctly, from this characterization technique. But we also used another characterization technique to reconstruct the strain directly from suspended nanostring devices, and namely we used the Raman spectroscopy. So basically, if you focus an intense visible laser on some region of the strained silicon on insulator chip, you will get, if you look at the Stokes shift, Stokes scattered light at lower frequencies than the excitation beam, you will see a spectrum that looks like this, with one intense peak at a red shift of 520 centimeter to the -1, which is basically the frequency of the main optical phonon of silicon without any strain, and a smaller satellite peak at a small redshift from the main peak. And the small satellite peak is coming from the thin film strained silicon layer. It's very weak compared to the main peak, because it's strained silicon is just around 12 nanometers thick. And the interesting part is that the redshift between the main Stokes line and this satellite peak is proportional to the strain in a way that is set by that can be found by solving this circular equation that relates the local state of the strain, or the local strain tensor, with the compliance coefficients or the stiffness coefficients of atomic bonds, basically. So the atomic bond stiffness depends on the strain state via some empirical coefficients that in general are difficult to predict, but for silicon, they have been measured many times, so are available in the literature. And the interesting part of this technique also is that it is spatially resolved, because you just translate you can just translate the excitation laser on top of for example, this nanostring corrugation, and you will get some wave vector frequency that depends on the position. You will get a frequency of this satellite peak, which is actually very intense if you undercut away the substrate. It's the main contribution to the Stokes scattered light. And you will see that the redshifted frequency depends on the position in a way that is related to that we expected, because we know that if we introduce a width corrugation in a suspended nanostring, we'll also get, and we started from uniform stress, we'll get in equilibrium a redistribution of stress. So the thick parts of the unit cell will relax to lower stress, corresponding to a lower redshift. And the thin parts of the unit cell, or the thin parts of the corrugation, will correspond to a higher stress, which corresponds in turn to higher redshift magnitude or redshift frequencies. And then we could use the empirical coefficients of the empirical strain stiffness coefficients to reconstruct the stress point by point, by also taking into account the local heating introduced by the laser. So we did that power sweep to extrapolate away very roughly the heating effect or the temperature effects due to the laser heating of the nanostring. So I showed you this width corrugation, and the width corrugation is basically the main ingredient essential to understanding this technique of phononic crystal based soft clamping that we use in the nanostrings. Because when you have a width corrugation corresponding to a stress a periodic stress modulation, what happens is that you perturb the dispersion relation for phonons traveling at megahertz frequencies, typically, depending on the period of the modulation. You can set very easily. And then basically you have a very high, this sequence of unit cells will reflect very strongly for these band gap frequencies that you can create at megahertz frequencies using the periodic corrugation of width. But if you perturb the translational symmetry of this width corrugation, you can introduce a defect in the middle of the string, and there you can localize a mode. You can have a localized mode which will decay exponentially in the phononic crystal regions. So it smoothly decays outside of the defect regions, and it approaches. It has exponential. I mean, it's suppressed exponentially before it reaches the clamping points. And correspondingly, if one computes the square curvature of this displacement pattern, you will see that the curvature at the clamping points is still pretty high, but it's extremely well suppressed compared to the case of the mode shape of just a uniform nanostring. It will have much higher curvature at the clamping points. Then, if you go back to the expression of the dissipation-diluted quality factor, we can completely neglect or almost completely neglect this first term that, if you remember, depended linearly on lambda, and we're left with only the second term corresponding to the distributed curvature of the mode pattern, which is this technique I mentioned of soft clamping in general, when we only have the dependence on the lambda square term at the denominator, and allows you to increase the quality factor of more than an order of magnitude compared to generic unpatterned nanomechanical resonators. Indeed, we were able to observe this kind of enhancement by doing an experiment of pulling down some high aspect ratio strain silicon nanostrings. Here we have a characteristic, or for this device, the length was about 6 millimeters, and the thickness was about 12 nanometers. And here we characterize all the quality factors of the different flexural, low order flexural modes out of plane of or transverse flexural modes of the nanostring. You could see that the localized mode inside of the bandgap had extremely high quality factor, around on average, or let's say the average value that we measured is around 13 billion. That is enhanced by more than 2 orders of magnitude compared to the resonances that are located outside of the bandgap. And this is even more than the expectation we would have just from dissipation dilution or the soft clamping effect. But as I will discuss later, we would have expected a smaller improvement just from dissipation dilution. And correspondingly, with the measured quality factor and the known temperature from, let's say, the readings, the thermometers placed in our cryostat, we could estimate the minimum force sensitivity or the minimum force that could be sensed by such a mechanical oscillator at 7 Kelvin. which is estimated to be about 50 zeptonewton in a bandwidth of for a bandwidth of 1 hertz, which is actually better than, as far as I know, all the atomic force microscopy cantilevers that have been used or demonstrated so far at the same temperatures. So all the points, just as a side remark, all these points of or all these different quality factors for different resonances, we measure them in such a experimental setup. It's a 50-50 infrared 50-50 nanometer infrared interferometer that we built for displacement, nanomechanical displacement measurements, and the only reliable, or as far as I know, the only reliable way to measure damping rate and quality factor for high Q, very high Q mechanical oscillators is by doing a ring down measurement. So basically, you drive on resonance on some resonance the mechanical oscillator using either a piezoelectric transducer or an auxiliary near infrared laser coupled to the cryostat. And then basically you cut off abruptly the excitation and you record the ring down of the amplitude over time. And the traces can last up to several hours for the highest Q devices. And here an important aspect is that we put a shutter to periodically shut off or close or suppress the probing beam and only measure the displacement of the mechanical oscillator at short intervals separated by large quiet times, let's say. This was very important because we could notice that when we probe the mechanical ring down continuously, we could really affect the mechanical damping rate in either direction. Either we made it lower or we made it higher by the interaction with the laser beam. And we didn't actually investigate this mechanism in detail, so we don't have a complete explanation for what it is. But from some evidence that we have gathered, it's probably related to some autonomous feedback mechanism due to the reflection, to the fact that part of the laser beam is reflected at the chip surface underneath the nanostring and create a standing wave that can introduce some feedback. In fact, we saw that if you change the position, if you change the displacement between the microscope objective and the chip, you could affect the sign or the magnitude of the damping rate. But yeah, for all the data points that I showed before and I will show later, basically we do this gated measurements to be as the least invasive possible for recording the mechanical ring down. So with the same nanostring that I showed before, we also performed the temperature-dependent measurement of dissipation. We selected 3 modes, 2 below the band gap frequencies, and the localized mode, the highest Q mode, localized inside the band gap. And we recorded their quality factor as a function of the temperature that we tuned by just using a heater placed inside the cryostat chamber. And we could see several interesting features. For example, the first thing we noticed is that around room temperature, the localized mode was partially gas damped. So quality factor was not purely due to the intrinsic properties or due to dissipation-diluted material properties of silicon, but it was partially set by random collisions of residual gas molecules in the vacuum chamber. So we couldn't get low enough pressure at room temperature to really recover the intrinsic quality factor or measure the intrinsic quality factor. And we saw this by introducing a little bit of gas in the vacuum chamber in a controlled way and measuring the quality factor as a function of the pressure we established in the vacuum chamber. But this mechanism of gas damping is very likely not relevant at all at lower temperatures, because at lower temperatures you start to get cryopumping effects in the cryostat and the pressure is dramatically reduced. You cannot, but it's not possible. It's very difficult to actually estimate what is the real pressure at the sample position at the lowest temperatures. Then the most prominent feature of this dissipation versus temperature curves is the presence of 2 minima at 120 Kelvin and at 170 Kelvin that we saw on both localized mode and out of band gap distributed modes. And for example, we can zoom in on the 170 Kelvin minimum and do a finer temperature sweep around this dissipation maximum. We can see that all the modes undergo this maximum of dissipation, and the temperature depends on the frequency, or the temperature of the minimum is proportional to the frequency, to the mechanical frequency of the mode. This allowed us to conclude that this dissipation maximum is most likely related to the presence of thermally activated two-level defects. So when the mechanical frequency becomes, when the temperature is such that the relaxation rate between the two levels, the two levels is equal to the mechanical frequency, you will get a maximum of the dissipation, and the mechanical resonance, the strain field of the mechanical resonance will interact maximally with the two-level defect. We could also recover from simultaneous fitting of these three curves a value of 0.2 electron volt for the potential barrier that separates this two-level system. That is similar to what has been reported for other nanomechanical oscillators in the literature. Finally, we can gather some more information. We can divide the quality factor measure for the localized mode by the quality factor that we observe for the recorded for the distributed modes, which is roughly constant for the two of them, as you see, and plot it as a function of temperature. And the trend is interesting because if it was just if this ratio was just set by dissipation dilution, you would expect practically a flat or very, very weak and slow variation with temperature due to the material properties changing with temperature. But it's not the case, and especially in some temperature ranges, you observe some very very rapid increase in the ratio, and this is probably an indication that the distributed modes start to be affected by phonon radiation losses as you lower the temperature. So they start to leak out energy, to undergo dissipation by leaking out energy to the substrate, which is a loss mechanism that is very effectively suppressed by the phononic crystal shield. Therefore, the localized mode doesn't undergo this acoustic radiation loss channel that much. And this means that it's a more accurate probe of the intrinsic quality factor of strain silicon, the localized mode. So for the future, something that would be very interesting to explore is going to even lower temperatures allowed by placing the samples in an environment of a dilution fridge, which can go down to some 10 millikelvin of base temperature. And this is particularly interesting because it has been shown many times in the literature that both amorphous materials, mechanical oscillators made out of amorphous materials, such as silicon nitride, but also crystalline materials will undergo an increase of the quality factor at between liquid helium and millikelvin temperatures. But crystalline materials have a much more rapid and strong dependence on the temperature in the millikelvin regime. And this is very commonly attributed due to the presence of two-level systems. So basically, defects or basically two close by minima in the energy landscape given by displacement of the energy in the thermodynamical energy landscape of the atomic lattice, given by displacement of a few atoms from the equilibrium position to another set of equilibrium positions. So you have two minima which are just separated by a very small energy difference. And the density of these two-level systems is predicted to be very, very high for glassy or amorphous materials, but should be much smaller for crystalline materials, which, but nevertheless, two-level systems are known to often set the dissipation properties of crystalline materials also, as it was here, for example, reported in single crystalline silicon measured at millikelvin temperatures in the 80s. but nonetheless, the effect of two-level system should be much weaker for crystalline materials because of the lower densities that one would have, for example, at grain boundaries or interfaces of the crystals. So, okay, this basically concludes the first part where I was talking about this, where I talked about this work on strain silicon mechanical oscillators. And then I will more briefly touch on some other techniques for improving the quality factor of mechanical resonators by playing on the dilution factor instead. So we introduce some more mode shaping engineering techniques that we have demonstrated typically in silicon nitride nanomechanical oscillators in our lab. So here I will talk about hierarchical branching as another method for soft clamping, which is alternative to photonic crystal based soft clamping. And to understand it, we can consider the case of a nanostring, which is not simply clamped to its supports, but it branches symmetrically in a basic element, which is a three-string joint. So basically, you branch symmetrically, and then you clamp after the branch. You branch of an angle theta. And the interesting thing is that the boundary conditions of propagation of elastic waves are such that the displacement gradient of the displacement gradient will be suppressed by a factor of cosine of theta over the three beam joint. So if we cascade several of these three beam joints, we can gradually suppress the amplitude of the displacement field going towards the clamping points, which is basically equivalent to soft clamping, because then you would get also much reduced curvature of the mode shape pattern at the clamping points, and basically get rid of this contribution, this dominant contribution for the dilution factor. To demonstrate it, we made this kind of fractal-like devices, which again present several generations of three beam joints. They were made out of silicon nitride, around 20 nanometers thick, and with a deposition stress typically of 1 gigapascal or a bit more than 1 gigapascal. And with this type of fractal-like devices, we also recorded very high quality factors, up to roughly 800 million at room temperature, and a bit beyond 1 billion at 5 Kelvin, so in the same crust that used for the previous experiment, which correspond to also force sensitivities that are better than the best AFM, the performance of the best AFM cantilevers that has been reported so far. We can also consider another type of mechanical structure that exploits the same basic element of a three beam joint, which is this nanomechanical polygon resonators. Here we have a polygon-like network of strings, which is suspended by some tethers, which keep it stiff and tensioned. And each of these joints, I mean, we'll have at each corner or each vertex of the polygon, we'll have one of these three beam joints. And basically, we consider perimeter modes, so modes that have the opposite type of symmetry as the previous case of fractal-like modes. So one thing I forgot to mention is that the main advantage of the previous structures is that, you can see it from here, is that we're able to soft clamp the fundamental mode rather than soft clamping or enhancing the dissipation dilution for a very high order mode, just as in the case of photonic crystal based soft clamping. And also you enhance to a lower extent also the lowest order, the lower order flexural modes. Here we don't soft clamp anymore the fundamental mode, but a rather low order mode, maybe with mode indices of below 10, let's say. If you count all the modes starting from the lowest frequency, because here we're considering modes that only propagate along the form a standing wave along the perimeter of the polygon, and they have the opposite type of boundary condition, antisymmetric at the three string joint. with this type of boundary condition, one can see that the bending of the tether is completely suppressed. It's zero, corresponding to, let's say, almost perfect soft clamping, if not for the fact that this suppression of bending comes with the introduction of torsion. So when you basically have this kind of boundary condition, it will cause a torsion of the tether during the period of oscillation. And this torsion is also a way to store energy, a lossy way to store energy, or contributes to the denominator of the dissipation dilution factor. Basically, it gives an additional contribution to the second term. But nevertheless, it's a contribution that scales quadratically in lambda. Just like the distributed banding or distributed curvature contribution. Therefore, we still have a soft clamped scaling. And we measure many of these polygon resonators. The performance of the perimeter mode is not very strongly dependent on the number of sides of the polygon or the actual, whether it's regular polygon or not. It gives pretty high dissipation dilution for a large parameter space. And moreover, for the envelope of this data points that we recorded of quality factor versus frequency, we see the 1 over lambda square scaling that is characteristic of soft clamping, as we expect. And it doesn't quite touch the clampest limit due to the presence of this torsional contribution, additional torsional contribution in the tethers, or also in the polygon sides. There is a little bit of torsion during the motion. The clampless limit, I should clarify that it's basically the limit of a sinusoidal standing, an idealized sinusoidal standing wave that you would have if you had totally zero clamping point curvature. Which is a case that cannot be recovered in real nanomechanical oscillators, because you always have a strong clamping point curvature due to having to respect clamped boundary conditions. And with this kind of mechanical oscillators, we have measured quality factors up to 3.6 billions at room temperature, which is, as far as I know, the record value for nanomechanical oscillators so far. Frequencies at frequencies which are intermediate between the case of phonic crystal-based soft clamping and of the fractal-like structure. So here the maximum was attained at 350 kilohertz. So a drawback of this polygon of this nanomechanical polygon structure is that it has low. You generally have low displacement sensitivity because you get low reflection efficiency when you focus light on one of the branches for recording the displacement of the nanomechanical oscillator. Because typically the width that we need for having a high Q resonance is in the range of 200 nanometers, which is very sub-wavelength. But we saw that we could introduce a small corrugation just in the center of the polygon sites, where increase the width from values which are sub micrometer to several micrometers, and correspondingly we improved a lot the reflection efficiency in measurements of displacement. Here recording this simple interferometer setup that I've discussed before. We can see that the corrugation is effective by scanning the laser beam over the polygon side and recording the sideband power for corresponding to the mechanical resonance to the perimeter mode mechanical resonance at each point, and we see a strong increase of reflection efficiency at the position of the corrugation. So much better displacement sensitivity for those positions. So having this high or improved displacement sensitivity, we also wanted to actually measure the force sensitivity that we previously only estimated or quoted or calculated. This experiment basically amounts to measuring and calibrating the thermal display or the Brownian motion or the thermal displacement of the mechanical resonance. And then if you calibrate it properly, you can refer it to the force sensitivity of the mechanical oscillator. But when we tried to do it, we couldn't do it in the simplest possible way because of spurious frequency fluctuations that these nanomechanical devices are affected by. So if you have, for example, temperature fluctuations in the lab, or laser power fluctuations, or setup alignment fluctuations, they all will couple to perturb the resonant frequency of the device, and to cause a frequency noise or a frequency drift, therefore smearing out the mechanical susceptibility. Sort of, you can see that the effective susceptibility in these measurements of the thermal displacement is much broader than the millihertz line width that is measured by ring down measurements, and correspondingly, we couldn't resolve the force sensitivity predicted by the fluctuation dissipation theorem, the thermodynamic limit of force sensing. In order to overcome this problem of frequency noise, we applied a simple method that basically amounts to recording the displacement of the mechanical oscillator and doing feedback cooling. That is, synthesizing a force with a piezoelectric actuator, for example, that is proportional to the velocity of the recorded displacement traces. And by having this out of phase force, you can damp the mechanical oscillator, and which amounts to, in the spectral domain, increasing its line width, broadening its line width, and suppressing the peak value of the thermal motion. It's basically an experiment of feedback cooling, of moderate feedback cooling in the classical regime. Then the susceptibility or the effective line width is increased from millihertz or sub-millihertz levels to, for this measurement, around 1 hertz, which makes the experiment much more tolerant towards these frequency drifts and frequency noise that always occurs in the nanomechanical devices. And correspondingly, we could record some force sensitivity traces, which give here, within the effective bandwidth of the mechanical oscillator, the force sensitivity that we recorded is around 1.3 Attonewtons in a bandwidth of 1 hertz for the measurement, which corresponds to the prediction of the fluctuation dissipation theorem. And outside of the bandwidth of, outside of the effective line width of the mechanical oscillator, it increases due to the fact that we're hitting the noise floor, the detection noise floor of our instrument, the shot noise level of the interferometer in our case. And the important side is that this feedback cooling technique, if feedback is not too strong, it doesn't introduce extra force noise. So it allows you to recover the thermodynamic force sensitivity of the nanomechanical oscillator. So with this, to conclude, with this, having these Polygon resonators with good displacement sensitivity, owing to the new designs with the corrugation pads, we saw that it should be possible to do feedback cooling close to the ground state, even without the presence of a cavity, just using a simple detection setup like vibrometer or interferometer, just by shining light of the beam and recovering and collecting and measuring the reflected light with good efficiency. This should be already, the numbers look okay or feasible if you assume a starting temperature or an equilibrium temperature for the mechanical mode around 10 Kelvin. Then you would have a phonon occupation around 1 million in equilibrium, and it would with the projected or with the measured displacement sensitivity that we had, this would allow us to cool down to roughly 10 phonons using the optimal strength of feedback cooling, which, for example, would allow us to see sideband asymmetry, mechanical sideband asymmetry. Yeah, and what you see here is basically just a proof of principle experiment on at room temperature, where we cool down from an occupation of 10, almost like more than 10 million to an occupation around 1,000 phonons with a simple optical feedback or radiation pressure based feedback. So with this, I conclude the seminar, thanking all the people that work with me in the lab on the project, and also the master students that are no longer working in our lab, Diego and Robin, which is actually now in TU Munich, I think, I was told. And yeah, if you have any questions, please shoot away. Thank you for the attention, by the way.